Hello, this is Team 3. Last week, our team discussed about how steel framing work was done for St. Mary X building. This week, our team will discuss the details of the node part of the diagrid and how could have reduced the tolerance. The St. Mary X building has a unique over appearance. How could it successfully be constructed a circular appearance using a diagrid structure? Also, to successfully construct a diagrid structure in a high-rise building, a very small tolerance is required. How did the building come up with a way to reduce tolerance in the construction process? After deciding the shape of the diagrid module in the building, determine the number of nodes on each floor according to the shape of each module and the height of the building. Then select the optimal angle within the possible angular range to determine the appropriate angle between each node. The St. Mary X building was planned based on a two-story triangular module. The number of nodes for 40 flowers is designed to rotate by 5 degrees as the core of each flower goes up. This made the node located at every two-story height, which became an important factor in deciding the number of nodes. The calculation procedure is as follows. The St. Mary X building's diagrid system used a triangular module designed based on the height of two floors. Each floor follows a plan that rotates by 5 degrees. This sets the angle of the two-story diagrid to a total of 10 degrees. The building's circular structure is divided into 36 radial beams from the core to the diagrid, and each two-story unit contains 18 nodes. Therefore, a total of 360 nodes were used on our 40 floors except the dome. In calculating the angle of the node, it is generally common to determine the angle based on the aspect ratio in the number of floors. But also design aspect and environmental factors can influence the determination of the diagrid angle. The St. Mary X building determined the optimal angle of the diagrid by considering the design aspect and its surrounding environment while considering structure stability. The appropriate angle was selected in the range of 35 to 90 degrees in the process. Therefore, as the height of each flower is the same, but the number of nodes on one flower is fixed, a variable angle load method has been applied, where the angle of the node varies depending on the flower slab area.
Node construction is the most important part of the diagrid. In order to efficiently deliver the horizontal and vertical loads of each floor in the Gherkin building, the nodes are constructed in a pipe plate transition type consist of a bolt combination of three integrally welded plates and hollow structure section. Gherkin building pipe plate nodes are made up of various members. The diagonal members and hoops add strength and stability to the integral structure of the pipe plate. These members effectively transfer the horizontal and vertical loads between the layers. In addition, the node is fastened with a radical beam that connects to the core. This radical beam supports the structure from the core to the diagrid and evenly distributes load on each floor. This serves to maintain stability and structural consistency across the building. In order to reduce the construction error of the node, the Gherkin building was used by combining CNC milling work and slot hole type bolt bonding. CNC milling enables precise processing of nodes with a tolerance range of 0.1 mm, and slot hole voltage joint provide accurate position and size slot holes to take into account and minimize errors that may occur during construction.
The steel construction of Saint Mary's building using Diagrid followed these steps: prefabrication, transportation, steel erection. These three construction processes occurred continuously and simultaneously.
Diagram structure of the Saint Mary's building was very important in the manufacturing and construction quality of precise steel members. Diagonal members and nodes were pre-made in the factory and transported to the site. Due to the small site, it was not possible to load all steel in advance, so they chose to continuously supply factory-made members to the site. Steel made at factories in the Netherlands and Belgium was transported to Dartford Yard in the UK, where it was supplied fully considering the field conditions. Two floors of steel were constructed every 2 weeks, and 4 tubes and 2 nodes were included in each delivery for 18 A-frames per floor. Factory manufacturing and precise management of field supply enabled successful construction.
The construction sequence of the diagram structure at Sarsen Mariax is as follows. It going in the order lifting, temporary tightening, precision check, and final tightening. Let's take a closer look at each steps. First, let's talk about the lifting process. When the huge diagram components manufactured in the factory arrive at the construction site, they are lifted up to the installation position using a tower crane. Now, once the components are in place, temporary tightening work must be carried out. But why is temporary tightening necessary? Temporary tightening plays a role in increasing the contact between components and maintaining a constant gap before the final tightening. In a diagram structure, the components must be in the exact position to effectively transfer the load. What would happen if we proceed with the final tightening without temporary tightening? Gaps may occur between the components, leading to stress concentration and deformation of the structure. It's also impossible to prevent increasing construction errors. By the way, did you know that accuracy is the most crucial factor in diagram construction? Even a slight error in the angle, length, or connection position of the components can greatly shake the stability of the entire structure. It's really critical. So, for precise construction, it's essential to thoroughly check for any discrepancies with the drawings. We must verify whether the diagonal length and angle of each diagram module match the design drawings. To do this, a precision check is necessary. Here's the important part. First, they establish a baseline and reference points, and accurately mark the installation position of each component. They mobilize equipment, like laser distance meters or total station, to align the horizontality, verticality, and height to the millimeter level.
Errors in vertical, parallel, and right angles that may occur during construction should be measured. Usually, the error is measured using a plumb bob to easily see the angle of whether the diagram members is erected vertical or not. After trying a thread to a well or filler, check whether the node is constructed at the desired vertical angle through the guideline on the floor. Additionally, a laser trench was used. The error in construction was measured by measuring the error using a geo laser transit through the core of the node's central extension line. In addition, through a very delicate design, there was little error, but when a slight error occurred, it could be solved through the slot hole bolt method that could be corrected.
Once it confirmed that the diagrid is in the correct position, they finish by tightening all the high-strength bolts. At this point, it's important to tighten to the specified torque. Through these processes, the diagrid structure of the solid-state reacts project could be assembled in the precise position. Today, we explored what factors were considered when designing the diagrid system used in solid-state reacts. We also learned about the process involved in constructing the diagrid structure. Next week, we'll explain about the control of solid-state reacts. Thanks for listening to the presentation.